We left off last week talking about subsets. We were talking about set theory. We had a lot of fun. Set theory is a lot of fun. We need to start here. We used this symbol here with the line underneath. We called that the subset symbol. This means A is a subset of B. We also argued last week that a set, every set is a subset of itself. We made that argument. We said it's kind of silly. It is true. The word or the prefix sub makes you think of something being smaller or dwarfed by or smaller than. So saying something is a subset of itself feels wrong. It doesn't feel right. You should always make sure to use proper prefixes or you'll be hunted down by the prefix mafia. That's an old joke. I don't think anyone in here might get that joke. Anyways, that's okay. Not a problem with that. Proper subsets, now those are what we are kind of thinking at when we use the word subset. A proper subset where you don't use the line underneath, just like being strictly less than. A proper subset can only happen if the sets aren't equal, if it's not the exact same set being repeated. That's what it means to be proper. It actually has, not only is it a subset, but it has less elements than the larger set, strictly less. And so we can see a few examples of that. We're going to write either the subset symbol or the proper subset symbol in the following to make a correct statement. So here's two sets, all X such that X is a person that lives in San Francisco. Well, San Francisco is a city in California. If B is the set of all people who live in California, then clearly A is a subset of B, because everyone who lives in San Francisco also lives in California in a more general sense. So we can use the regular subset symbol. This is perfectly valid. It also turns out that while A is a subset of B, A is also strictly smaller than B. There might be, I don't know, 5-ish million people who live in San Francisco and its suburbs and all the areas around, but there's over 50 million people who live in California. So A is a subset of B, but it's also a proper subset of B because it's not the exact same set. It's strictly smaller than the set B in this case. So I can use either one of these symbols, just the subset symbol and the more strict proper subset symbol here. I can use either one of those and be perfectly happy. Now down here, you have the set 2, 4, 6, 8. It's missing the who do we appreciate part. That's okay. Then you have this set 2, 8, 4, 6. But they're the same set. They just have reordered elements. So A and B are exactly the same. A is equal to B. So two sets that are the same are still, one is still a subset of the other. That's always going to be true. You are always a subset of yourself. But that's the only symbol we can use. We can't use the proper subset symbol because the set A is not lesser than in size of the set B. It has the same cardinality. So it seems like we're kind of splitting hairs. You'll notice the regular subset symbol kind of reminds you of the less than or equal to symbol. And that's actually a good comparison because the or equal to part makes sense here. It's still a subset if they're the exact same set, if they're equal to each other. But when you use just this without the line underneath, this is the proper subset symbol. That kind of looks like just the less than sign and only the less than sign. And so it has to be strictly smaller in size, and that actually makes sense. So there's a real good comparison between these things. Now we are going to really kind of rack our brains here there's a little rule that says the empty set is a subset of any other set. And I kind of hate, I have to say the word set a lot. I'm saying set, 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 set. And it kind of, it jumbles what I'm saying, and it kind of makes it a little bit confusing if you ask me. But at any rate, the empty set is a subset of every other set on the planet. I'll even write that out. The empty set is a subset of every other set on the planet, including itself. This is like a bad Arnold Schwarzenegger movie where he clones himself and there's like 5 of him running around. Or if you've ever seen Michael Keaton in Multiplicity, it's just a confusing mess. And no, neither of you, you've probably seen that movie, Michael Keaton, Multiplicity, 1996. Also had Andie MacDowell from Groundhog Day. She's great. Anyways, you kids like movies that I saw as a kid. Anyways, so the empty set is a subset of every other. Now, as long as you have the set B and it's not empty, as long as it has something in it, the empty set is a proper subset of that, because the empty set now would have less elements than that. I like Groundhog Day. Groundhog Day is an amazing film. It has some pretty interesting philosophical elements to it while still being entertaining. Yeah, Groundhog Day is fantastic, and Andie MacDowell is in that film. She's the the love interest, the main female in the movie, and Bill Murray is the main character. Bill Murray's great. I watched the original Ghostbusters again the other night. If you've never seen Ghostbusters, go watch it. And I kind of watched it as a kid, but as an adult, it's hilarious. I was cracking up the whole time. Bill Murray is just a complete jerk, and it's funny. He's a funny jerk. And then, so anyways, yeah, that's kind of a side tangent. I love movies, and I don't really like artsy, stupid movies. I like fun movies that everybody can like. So anyways, so we got subsets, we got empty sets, we got proper subsets, we got all these terms floating around. So I'm trying to make it as simple as I can, but there's just, sometimes you just have to use the vocabulary, the verbiage that they give you, and that's just life. So we're just going to kind of keep this in mind as a fact. The empty set is a subset of all other sets, no matter what you pick. Now we have to go to another level. We have to go to the next level. The number of subsets of a given set. The number of subsets of a given set. Think about the empty set, the set that has nothing in it. It has no elements in it. The only thing that could possibly be a subset of the empty set is the empty set itself, because all sets are automatically subsets of themselves. And the empty set is automatically a subset of every other type of set. And let me reiterate, I'm getting tired of saying the word set. It's starting to feel like a buzzword, but that's it. So if your original set's the empty set, the only possible subset of it is the empty set. And that's only one possible subset to it. Now you might think, who the heck cares about counting up the number of subsets of something, blah, blah, blah. But it actually turns out that in probability theory, which we're going to be touching on towards the end of this semester, you would absolutely want to be interested in that. Think about a standard deck of cards. How many cards are in a standard deck? 52. You've got your aces, your twos, your threes, your fours, all the way up to your kings. You've got 4 suits in a deck of cards: hearts, clubs, diamonds, and spades. Well, if you've ever been to a casino and played some blackjack, you can play some poker at a casino. Or if you just enjoy playing card games, if you like playing Go Fish, there's nothing wrong with Go Fish. If you could turn it into a gambling game, I'd be there. I'd gamble on Go Fish. But in a standard deck of cards, if you're just playing regular, good old-fashioned poker, regular 5-card hand poker, you have a 5-card hand, and if you think about it, the whole deck has 52 cards in it. What you're holding, since you're holding 5 of those cards, you're holding a subset of the entire deck of cards, if you think about it. Now, if you're playing poker, you want to know how you should be betting. Oh my, I've got a royal flush in my hand. That is the best hand in poker, a royal flush. There are only 4 possible royal flushes in the deck. The number of subsets that have 5 elements in them out of the 52 card deck, that is the number of possible 5-card hands in poker. It's almost 2.6 million. So if you're calculating probabilities, you would need to know, oh, well, there's only 4 possible royal flushes out of 2.6 million hands that are possible in the deck. So a royal flush is extremely rare. A royal flush is practically impossible. It has a 4 in 2.6 million chance of occurring. So this is actually where thinking of subsets starts to make a little bit of sense. Oh, if we could talk about probability theory, if we could calculate probabilities, yeah, now we're cooking with fire. So it's so abstract right now. It's so hard to like give hard and fast examples here. That is one of the challenges of math. I completely agree with that. Is that math is just so abstract. It's just so out there, man. It's like artistic, bro. It's very difficult to wrap your mind around. But the more you learn, the more you start to see examples of things, of concrete examples of where this could take place. So if you start with a set that has 1 element, let's say you have the set containing just the single element, the letter A. The letter A has 1 element in the set. Now all of the possible subsets of that. Well, every set is automatically a subset of itself. So the set containing A is a subset of itself. But another subset is the empty set. Thus, there are 2 total possible number of subsets for an original set that only has 1 element in it. Go down the line, start with a set that has 2 elements in it, A, B. It's got 2 elements. There's 4 possible subsets. The original AB set itself, the A set, the set containing just the letter A, that's clearly a subset of AB. The set containing just B, that's clearly a subset of AB. And then the empty set by default. And now you have 4 possible sets. And then if you got ABC, if you have a set with 3 elements in it, ABC, it's easy as 1, 2, 3. The number of possible subsets, well, let's list them out. You can have the original set itself, that's always true. Then you can have the sets with any 2 elements in them. So you can have the set with AB in it, AC, not the Slater variety, and BC, not the time period. You can have these, and then you can also have the sets that have exactly 1 element in them. And then finally, you can have the empty set. So it's kind of a weird pattern that's starting to form. The number of subsets is doubling as I increase the number of elements by 1. In fact, there's a nice simple little rule. The number of subsets of a set with 0 elements is 2 raised to the power of 0, which is 1. Remember, raising anything to the 0th power is 1. The number of subsets of a set that starts with 1 element is 2 to the 1st, which is just 2. Raising to the 1st power does nothing. The number of possible subsets for a set that has 2 elements in it is 2 squared, which is 4. The number of possible subsets for a set that has 3 elements in it to start with is 2 to the 3rd power, which is 8. It's a neat little pattern that's forming. And it's something that's super interesting to people who like to count things. And counting things is very important in mathematics, especially probability theory. And so if I started with a set that had 5 things in it, A, B, C, D, E, the number of possible subsets would be 2 to the 5th power, which is 32. There'd be 32 possible subsets. So that's kind of interesting. Lastly, the number of proper subsets of a set with n elements is 2 to the n minus 1. Because think about it. It's normally 2 to the n. 2 to the power of how many elements are in the original set is the number of possible subsets. Proper subsets, though, always knocks out the set itself, the original set you start with. So you got to knock that off by 1 if you're talking about proper subsets. But everything else is a proper subset. So lots of fun stuff happening. So what we're going to do in true Groundhog Day fashion, since we just talked about that movie, we're going to restart. And we're going to do the same lesson over again, just like in the movie Groundhog Day. No, I'm just kidding. If you've ever seen Groundhog Day, it's about a man played by Bill Murray, an all-time comedy legend, who every time he goes to bed, he wakes up and repeats the same day as before. And he's the only one who realizes it and has memory of it. And it's a pretty funny movie. That's all I have to say about that there, Pilgrim. So for instance, we already kind of verbally did this example. If you had a set with 5 elements, A, B, C, D, E, or maybe those 5 elements are the best 5 states in the United States. Texas, Texas again, Texas, no, if you had maybe Texas, what's another cool state? I like Maine. Maine is a really cool state. If you've never been to the Northeast, you should go. It's a lot of fun. It's very peaceful. New Hampshire, Vermont, and Connecticut. Those are 5 states. So any set that has 5 elements to start with will have 2 to the 5th, that same 5, 2 to the 5th, or 32 possible subsets. And then if you want to know the number of proper subsets, you got to throw out the set itself, because that one's not proper. So you just got to subtract one of them away, and so there's 31 proper subsets. If the original set you're starting with is all natural numbers between 9 and 15 inclusive, then just think of how many elements there are. You start with 9, you go 9, 10, 11, 12, 13, 14, 15. And if you just count, you'll see there's 7 elements in that set. So even though the set isn't directly spoken to you, it's not told to you exactly how many are in there, you can still count however many elements are in there. So there's 7 elements in this set. Thus, there are 2 to the 7th, or 128 possible subsets of this thing. And then just knock one of them off, and now you have 127 proper subsets. 127 proper subsets. Yeah, and so obviously it becomes impractical to list them out. You only have 7 things in this original set, but there's 128 possible subsets. Yeah, that's just how the math works out sometimes. It's actually really interesting. There's an old problem, like if you have you and 9 other family members, so there's 10 total people that are going to take a picture together. You want to take a picture with your family, but if you're curious as to how many different ways you could arrange the 10 people for a picture. So, okay, maybe, all right, we'll put Pop here on the far left, and then Ma next to him, and then cousin It and Uncle Fester we'll put next to them. It's the Addams family, obviously. But if I'm arranging these 10 people, and then I want to know all the different ways I can arrange 10 people. What are all the different ways? This is I'm going off on a tangent. What are all the different ways you could arrange 10 people for a photo? How many different ways would you guess, ballpark? You can throw out a guess in the Zoomosphere here in the room. How many different ways? You think there's 500 different ways you could arrange 10 people? 100? How many are you thinking? Maybe even 1,000? What are you thinking? You got a guess? No, it's massive. It turns out the calculation you do is this. In fact, we're going to learn that later on in this semester. It's called the factorial calculation. And oh my goodness, it's 3,628,800. Just 10 people. Yeah, it's wild. It's wild. But the number of different ways you could reorder 10 people into a different ordering than before is over 3.5 million different ways. So just because you don't have a ton of objects, 10 people, doesn't mean you can't create massive numbers of things you can do with those 10 people. So you're not going to get that photo. You're not going to get a photo of each of the possible arrangements and then get to go pick later which one you like the best. It's not going to happen with 10 people. Maybe with 3 people. With 3 people, there's only 6 possible arrangements. But each time you add another person, you are growing it at a very high rate. 4 people, there's 24 arrangements. 5 people, there's 120 arrangements. 6 people, there's 720 arrangements, and so on. But we'll deal with that later on in this semester. We'll get into that. We're not going to get into that. Nope. I don't care about that. Not important. Okay, so that will cover section 2.2 there. Very nice, very nice. We're just kind of getting through chapter 2 here. We're almost done. We got one more section of chapter 2. Chapters 2 and 3, and then also chapter 8, which is our finance chapter. These are just, this is what teaching math's all about. You get into some theory. I get to teach you some things you probably haven't seen before. A lot of 0332, the course we already finished, a lot of it's fractions and adding numbers and counting crows. And we've kind of worked with that knowledge before. And it's, it's something you've seen. It's good to get a brush up on it. Maybe you did learn a few new things here and there. But from the perspective of the person teaching it, it's like, well, that's a lot of math that I've done a lot before, but getting to teach this kind of stuff, you don't get to teach that every day as a math instructor. And so it's fun. It's nice, nerdy fun. Very nice high five. Great success. Indeed, much success. I assume you're making a Borat reference, which that is coming out, next month, right before the election? The new Borat movie, which I'm excited about. 23rd, October 23rd, very nice. Or November, excuse me. Okay. I'm not going to attempt a Borat voice because it would just be embarrassing. Hey, everybody, I'm the guy Borat. You ever seen my movie? It's called Borat. Go see the movie. That's my Borat voice. Thank you for the laugh, the slight chuckle. All right, so we're ready to move on to section 2.3. Section 2.3. Okay, so we're going to be talking about certain set operations and Venn diagrams, and this is actually going to be the meat and potatoes of chapter 2 here, is this section. So we won't go uber into detail with it. Venn diagrams are nice. Venn diagrams give us nice visual representations of sets of things, even if we don't write out all their elements explicitly in a set. We start by defining something called U, the universal set. This is the set of all possible things that you could be, that are of interest in a specific problem or application. For instance, let's say you're doing a math problem that you want to talk about a universal set, and all you care about are positive whole numbers, the natural numbers. Well, your universal set should not include more than just the positive whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, even if you don't use every single one of them. So that's pretty important to define a universal set, especially when we talk about set complementation, which we will hear in just a little bit. So let's say you have a universal set. Let's say you have a universal set, and the 5 elements in that universal set are a square, a triangle shape, the dollar sign, a capital M, and the number 5. There's probably an Agatha Christie novel out there utilizing this set. The set A, the set capital A, is just the square and the triangle. This set A always has to be a subset of the universal set. Universal set lists everything of interest, nothing more or nothing less. So the set A, you can't pull another element out of your hat and say, what about the letter K? Oh, it's not there. It's not in the universal set, so it's not allowed. A visual representation of this, the entire box is the universal set. That's going to be the set that has everything of interest in it. I'm going to use a U here in the top left corner. The set A is going to be a circle within that box that contains its elements. Now, we may not always write explicitly the elements in the Venn diagram, but we could. So here's set A. It's got the square and the triangle exactly as the set A lists. Thus, the dollar sign, the capital M, and the number 5 are all things that are outside of the A circle, but still have to be in the universal set. Everything has to be in the universal set. This means that the elements of the universal set that are not in A are the dollar sign, the capital M, and the number 5. These are the things outside of A. In fact, we are going to use a special symbol. I guess I'll italicize it. I'll make it nice and fancy. We're going to use the letter A with an apostrophe next to it. We're going to call that A complement. Yeah, E. Yeah. A complement. It's the complementary set. It is the set that is not at all has anything in common, but the two complement each other and fully create the universal set out. Now, most of us like to receive a compliment. If you're out in public and someone comes by and says, "Hey, you look real sharp today," I would say, "Well, thank you very much." And they would say, I don't have a joke for that. I don't know. Sometimes I just start jokes and I don't really go anywhere with them. So a compliment, you see that apostrophe next to it? It's a compliment. Another way to write it, if you can do superscripts here, is to write it like a C as an exponent. I don't think PowerPoint will do superscripts. Well, no, it will. This is another way to write a complement, is to just use a C like it's an exponent. But the way we'll likely be doing it is to just use an apostrophe, a complement. Cool story. So there's a couple kind of different Venn diagram representations that we can use here that are pretty gosh darn useful. If you want to represent disjoint sets are sets that have nothing in common. They have no overlap. Thus, when you draw the circles in the Venn diagram, they are not overlapping. They're next to each other, but they keep a safe distance. These ones are their social distancing for COVID, and I'm sure that joke has not gotten old at all. But yeah, they're keeping distance from each other because they have nothing in common. Proper subsets, if A is a proper subset of B, then A can be completely found within the elements of B. But A also has to be smaller than B. It has to be a strictly tinier set. So we can illustrate this by putting the A circle inside of the B circle and making it smaller than the B circle. That's how that'll work. So proper subsets. If two sets are equal, I guess you would just draw a single circle and say this is both set A and B. Probably not going to see that in practice. It's probably not going to happen. But finally, this is the most common type of Venn diagram you'll see here. This is what you think of when you think of a Venn diagram. You think of this guy right here, or gal. Yes. You have your box, the universal set. You have the two circles overlapping because you are notifying, or whatever, you're acknowledging is what I meant to say. You're acknowledging the fact that they could have some things in common. They could both share certain elements, and then they might also have their own space. They have their own space that they can carve out for themselves. So I'm going to illustrate this. In green here, I'm going to try and draw in the green space. Ooh. No. Well, okay, imagine I didn't get anything over here in this middle space. In green, you have elements that are only in A, not also in B. That's what green's gonna mean. Over here in red, why are you still green? I turn you to red. In red here, you're gonna have elements that are only in B, not also in A. And as you can imagine, in orange, orange because Halloween's coming up and I'm super excited about Halloween. My house is super decked out to the max with Halloween decorations. We've got a skeleton guy who's chilling in a cauldron like he's taking a bath. We got like another cauldron that you put water in it, and there's a water mister you can buy, and it mists all the water and it makes it look like bubbles and stuff coming out of the cauldron. It's really cool. We have a graveyard set up in our front yard. I love Halloween. In orange, and oops, let's see. Well, anyways, it decided to change the color right there. In orange, that's going to be confusing. You're going to have the elements in both A and B. And then finally, if you want to shade everything outside of that, in maybe yellow, and I'm not going to go all the way through it, but in yellow, you have elements that are neither in nature, no, that's not how you spell it, neither in A nor B. Everything outside those two. But while there's only two sets here, you have the set A and the set B, what that does is it creates four distinct regions on the graph. The yellow region, the red region, the orange region, and the green region, which is an important thing to remember. Anywho, this is going to be one of the most common ways we can represent these things. And so this will be how we see a Venn diagram, mostly. So let's say we have a universal set, the set of all elements of interest. And the universal set is the first 7 letters of the alphabet, A, B, C, D, E, F, G. Let's say the set capital B, and this is why we use a capital letter for sets, and for elements, we usually don't like to use capital letters. Though they are allowed, we try to differentiate. The set capital B consists of the elements D and E. So notice that here what we see is that D and E are elements of B because they're both in the B circle. One of those elements is in the B only area. Another one of those elements is in the area that's also in common with the set A. The set A then is all of A, B, C, D, and these Roman numerals are just to split up the different regions, distinct regions of this universal set. So the set A can be written as the set, I'll just write it out. The set A is the set containing A, B, C, and D as well. Don't forget the D because D is still in the set A. It just is also in the set B. They're shared. They have shared custody of the letter D. The set of elements in A but not in B, that would be this region here. Region 1 according to the Venn diagram. Oh, look, it looks like a crescent moon. And so that would be the letters just A, B, C. So it's pretty important to keep this in mind, how Venn diagrams work. It's going to be a very useful skill we're going to use to articulate some of these sets here. So based on this picture, again, let's keep answering questions here. Why? Okay, good question. Cameron asks, why is the D in the middle if it's with B? It's because this representation, the things in the middle are, it's not really something that's exclusive to either set. It's saying it's the overlap. It's what both set A and set B have in common. So set A is this entire circle. Set B is this entire circle over here. And then they happen to overlap. They happen to have some elements in common, namely the lowercase d element. So this D is found in both set A and also in set B. Now this 1, 2, 3, 4 business, those aren't actual elements. Those are saying this is one distinct region right here. This thing, just the lightly shaded blue region of A, this is one region. This over here is another region. And so the region, the 2 region, represents that which both A and B have in common. Does that make sense, Cameron? Cool. So yeah, it's not a representation saying these are all exclusive. The D gets to, go out with both A and B. So we can ask some more questions about this. The set of elements in the universal set that are not in B. So we need to exclude everything, every element that's in the B circle. So we need to throw out D and E. And what that leaves is A, B, C, because they're not in the B circle at all, as well as F and G, because those are not in the B circle. So the set of elements in U that are not in B is A, B, C, F, G. You ignore the things that are in B. Using some terminology we're just now about to start using in just a moment, you could say that's B complement. You could totally say that. B complement is what this set is. Finally, the set of elements in both A and B. Well, it's the only thing that is in both A and B is the lowercase d. That's what they share. So the word and is kind of a key word here. And what we're about to see is that we can use the symbol A. We're going to use an upside down U, B, and that's A intersect B. That's how we read that. It's the intersection of both of those two sets. When two things intersect, it's where they're have in common. You think about the intersection of Boardwalk and Park Place streets. The intersection itself is like a nice little square, maybe in the middle of a big area. And that little square, if you're standing in the middle of the intersection, you're on both Boardwalk and Park Place at the same time, if you think about it. Now, don't stand in the middle there because, Boardwalk and Park Place are probably very busy. but that's the idea of the intersection. So we've danced around it already. I kind of already have introduced the idea, but let's formally talk about it. The complement of a set. The complement of a set. Now, before we start this one, how many of you guys want to hear a joke? Raise your hand if you want to hear a joke. Out there in the Zoomosphere, let me know. Do you want to hear a joke? Comment yes. Yes, we got some yeses in there. Always, yes, always Coca-Cola, in fact. Always want to hear a joke. Okay, I apologize in advance for this joke. All right, so the guy walks into a bar. He sits down at the bar, orders himself a beer, starts drinking the beer. He's just sitting there having a good time. Maybe he's watching the sports game that's on. Maybe he's watching a little Sunday night football, or maybe he's watching Monday night football and seeing the Cowboys without Dak Prescott get absolutely obliterated last night. That was a horrible game. Anyways, he's sitting at the bar, and all of a sudden he hears, "Hey, your haircut, your recent haircut looks pretty good on you. You're looking solid today, sir." And he looks around and he doesn't see anyone. The bartender's at the other end of the bar serving other people. It's COVID-19, so the bar's kind of probably pretty empty-ish or something like that. And he doesn't see anyone around him. So he just thinks maybe he heard it on the weird TV on the other side of the bar. So he goes back to drinking his beer, and he's just enjoying it. And then he hears again, "Is that a new pair of shoes? Those pair of shoes look sharp on you there, mister. It just really works for your overall look." And the guy wants to turn around. He wants to thank someone. He wants to thank someone for saying such kind things to him. But there's nobody around. And he's ruled out other TVs because the only TVs on are the Cowboys game. And it's just a depressing thing. No one's saying anything nice about the Cowboys game. So finally, he flags down the bartender. He says, "What's going on here? I'm hearing all these nice, wonderful things that people are saying." And so the bartender grabs a little bowl of peanuts next to him. And the bartender says, "The peanuts, they're complimentary." Yeah. Allow 10 seconds for station identification. Yeah, that joke's not very good. But you know what, folks? Just because you know your joke's not going to be funny, you present it in a way that is funny by making fun of how bad your joke is. That joke was terrible, right? Yeah, you guys are all nodding your head. Like, don't nod your head too much. Just nod your head a little bit in light agreement. But yes, that joke was terrible. But you know what? I've never promised to be very funny. So I apologize for that joke now. Anywho, back to it. The complement of a set, which we've talked about, it's that apostrophe we put next to it, is the set of all elements still in the universal set. So everything still has to be in the universal set. Everything's still got to be there. That are not in the set A. You can use this set notation, and it's a little bit cumbersome, but okay. A complement is the set of all elements X, such that X is still in the universal set, but also X is not an element of A. It's outside of A. So if you have the universal set as your box, and you have the set A here, the complement of it would be this area outside of the circle that is shaded here. That's what a complement would be. This also brings up a great reason to have a universal set, to really narrow your focus on what you're talking about in general. Because if I didn't have a universal set, let's play a little fun game here. Without a universal set, let's say you had the set A, and it was the first 5 numbers, first 5 whole natural numbers. 4, 5. That's your set A. It's nice and clean. But you haven't defined a universal set. You're tempted to say the universal set should just be the natural numbers. That's all you're talking about. But we're not defining a universal set. So the set A complement, that looks bad, hold on. The set A complement is everything that A is not. It's everything outside. So you could say, well, yeah, it's the numbers 6, 7, 8. But wait a minute, it's everything. You haven't defined a universal set to hone in on. So it can also be ugly numbers like 9.5. Pi. Pi is an ugly number. It can also be letters of the alphabet, A, B, AARD, VARK. It could be weird symbols. Ooh, I don't know what this is. That's like the ocean. That's another element of a complement. What are some other things that we can put here? Oh, I don't know. How about every possible dollop of matter in the entire known universe, or even other multiverses or other dimensions where things and events played out differently? So how about a blockbuster from the year 1997? That would be in this set here. What are some other things that would be in this set? Every single hair on your head would be in this set. It's literally everything in the entire known universe except for the numbers 1 through 5. Okay, so clearly that's absurd. We need to define a universal set, U, so we just zoom in on what we care about. We're just focusing on the things we care about and not, weird symbols. So when we talk about the complement, we're talking about things that are not in our main set A, but they still got to be in the universal set. We don't want to go wild with it. So let's look at this example. Let's say you have your universal set, and it's the first 9 whole numbers, the first 9 natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. So anything you find, no element can be the number 10 or 11 or 12 because your universal set is honed in on this. Let's say A is the set of numbers 1, 3, 4, 7. Okay, sure, that's fine. A complement then would be the set, so the complement is still a set, it creates a new set. It is the set which is outside of A, but still elements of the universal set. So let's see, A complement, we can't use 1 because that's an A, but we can use 2. We can't use 3 or 4, but 5, 6, skip over 7, 8, and 9, which is exactly right. 2, 5, 6, 8, 9. It's the elements not in A. If you wanted a nice visual representation of this, look, here's your universal set. In set A, you have those elements, 1, 3, 4, 7. But clearly, the universal set still needs to have the elements 2, 5, 6, 8, 9. Those would be outside of A. Thus, A complement would be the set containing 2, 5, 6, 8, and 9. So one thing to keep in mind is that whenever you take the complement of a set, that new thing you're creating, A complement, is itself its own set. It's a new set. So we're going to learn that when we do some of these operations, complementation, we're about to do intersection and union, we're creating new sets out of these. Okay, let's take our break. Let's take our break. So we've been talking about sets, different kind of sets. We've discussed the set complement. Now we can talk about intersection. Now an intersection of two sets is going to look a lot more complicated here than it actually is. We use an upside down U. That is our set intersection kind of symbol. And it's a lot like, if you use the addition symbol, multiplication, subtraction, division, it's just a symbol telling us to do a certain operation. What this symbol does is it collects all the elements that are found in both A and B. In other words, the intersection finds that middle slice that A and B share on the Venn diagram. So if we took the set 7, 8, 9, 10, and 11, and we intersected it with another set, 6, 8, 10, 12, we are looking for two sets, or rather, I'm sorry, we're looking for all the elements they have in common. And it looks like they've got 8 in common and 10 in common, and that's it. So the intersection of this set with this set is a new set, 8, 10. So remember, doing an intersection, a complement, a union that we're about to see, all of these just create new sets. They're still sets. If we intersect this 1, 3, 5, 7, 9 with 2, 4, 6, 8, well, they've got nothing in common. This is some odd numbers. These are some even numbers. You intersect them, they got nothing in common. Thus, the answer is the empty set, which is still a set. And then if you intersect the set of these odd numbers, 1, 3, 5, 7, 9, if you intersect it with the empty set, well, these two things have nothing in common. These two things, they've got nothing in common, no common ground to start from. So the answer is also the empty set. Really, if you intersect any set with the empty set, the answer is the empty set. There's nothing in common, no elements. So the intersection's interesting. I believe there's a Venn diagram demonstrating it. Yeah, that's fine. So we have complementing, we have intersections, and now we have unions. Union is exactly what it sounds like. It's two sets brought together into one, basically. And the word to think about is the word or. And actually, secretly, or in math means and/or. That's how we use or in math and logic. We don't mean that if you say A or B, you mean it's things that are strictly in A or B, but not in both. No, you mean all things that could be in both or just any one of them. It's the most inclusive thing allowed. So there we go. Now we use a U symbol to represent the union of two sets. And what we're going to do is instead of trying to find what they have in common, we're going to say, everybody's welcome to the barbecue restaurant. We're going to say that every element that is found in either of the sets is welcome in both. And look, 8, the number 8 was in both of these sets. So it certainly makes it into the union, but we don't need to represent it twice here. If something's in both sets, we only represent it just once. 10 is in both sets, but in the union, it's still in there, but you only have to represent it once. Remember, sets don't need repeated things. This set here, 1, 3, 5, 7, 9, unioned with the set 2, 4, 6, 8. Remember, they had nothing in common. So their intersection was the empty set. But their union, we just slap them all together in one big happy set, and we call it a day. So the union and the intersection are just totally different. They're totally different. And then if you take this set 1, 3, 5, 7, 9, and you union it with the empty set, you're taking all the elements of here make it in. So all of 1, 3, 5, 7, 9 make it in. And then anything that would have been in the empty set also makes it in, but there happens to be nothing in it. So you don't have to worry about anything from the empty set coming in there. So the union kind of works like this. Think about going to a bar, and some of you aren't old enough to go to a bar. And I say you probably shouldn't then if you're not old enough. And we all know that there is no way possible out there for you to get into a bar if you are under 21 years old. There is nothing on the planet you can do. Anyways, imagine you have a bar. Now, some bars will let you in if you're 18 and up, but they'll take the Sharpie and they'll draw X's on your hands and they won't let you drink. That tells the bartenders don't serve these people, these youngins. Then there's other bars that will only let you in if you're 21 and up. Then there's also another rule we could apply. There are some bars who maybe they have a musical act going on that night. They have a band playing. And so the band is playing. They're going to charge you maybe like a $10 cover for everyone who wants to come in. These were in the olden days before COVID-19. We couldn't really go to bars anymore. So let's say you go to a bar, they have a musical act going on, and let's say that that bar only lets you in if you're 21 and up. So that bar is going to be the most exclusive. You have to be in 2 different sets to get into that bar. You have to be in the set of 21-year-olds or up, 21 or up. People always ask me, well, when I was younger looking, they said, are you 21? Can you drink this? And I'll say, no, I'm 25. So that's sarcastic. Anyways, the set of all people who are 21 and up. You also have to be in the set of all people who have and are willing to spend $10 to get into the bar to pay the cover. So in that case, the only people allowed in the bar are the people in the intersection of 21 and ups and people willing to pay $10. So that's an intersection. Those are the only people in that bar. However, some bars are a little more inclusive. Some bars will allow 18-year-olds in. You're just not allowed to drink. They'll allow 18-year-olds in, but here's the thing. They want to charge you a cover. Now, some bars are a little more lax about that. They say, well, look, as long as you're old enough to drink, we won't charge you a cover because we expect that you're going to buy some drinks here in the bar, and we're going to make we're going to make money off you that way. But if you're 18, 19, or 20, and you're not allowed to drink, we got to get some money off you somehow. So we're going to charge that $10 cover if you're not old enough to drink. So now all you have to do is be in the union of the set of all 21-year-olds and over, or the set of all people willing to pay $10 to get in. You just have to be in the union of that set. And then we'll say the universal set is all adults. So you still have to be at least 18 to get in. So that's kind of the idea. The intersection is more, it's harder to get into the intersection. But the union is a lot easier to get in. So just a few interesting consequences. If you take any set A on the planet, doesn't matter what it is, and you intersect it with the empty set, what does it have in common with the empty set? Nothing. They don't have anything in common. And this isn't necessarily a rule you have to memorize. Logically speaking, this rule should be pretty self-apparent. You intersect with the empty set, well, the set A is going to have no elements in common with the empty set because the empty set ain't got nothing in it. If you union the set A with the empty set, well, the union says everything in set A has to make it in, and then everything in the empty set also would have to make it in, but there's nothing that the empty set is contributing. But A still contributes all its elements, so it turns out that ends up just repeating itself and being the set A. Well, you know what this kind of looks like to me? You know what this looks like? What happens when you multiply a number by 0? You get 0. What happens when you add 0 to a number? Nothing happens. You stay with your original number. Hey, that looks a heck of a lot like this, and you know what? That's a very good observation. I'll pat myself on the back for making that observation. This is kind of similar to if you take any number x and you multiply it by 0, you get 0. But if you take any number x and add 0, you stay with the original x. That's kind of similar to what's going on. It's not exactly the same, but it's a similar idea, and it's a good comparison. And now I'm drinking my NOS energy beverage, so like I'll have so much more energy. Oh. All right, so performing set operations. Some problems involve more than one set operation. Always begin by performing any operations inside parentheses. So this is actually pretty interesting. You'll remember back at the beginning-ish of 0332, we talked about order of operations. If you got add, subtract, multiply, divide, all kinds of funny business with a bunch of different numbers. We defined an order in which you're supposed to do what? When do you multiply? When do you add? We talked about an order of operations, and at the top of the food chain for order of operations was anything inside parentheses. Parentheses pretty much got first dibs when it came to order of operations. That was the first one. Then it was exponents, which we're not quite going to have, in this case. So, example, performing set operations. Well, A union B inside parentheses, then we're taking the complement of that. So let's look. The universal set here is the numbers 1 through 10, the whole numbers. The set A is just the numbers 1, 3, 7, 9. There's maybe no real relationship between them. That's just a set. The set B is 3, 7, 8, 10. If you wanted to find A union B complement, A union B is in parentheses, so it goes down first. Then you take the complement of that. So A union B here, I collect all the elements that are found in A or B. I don't need any repeats. So it's going to be 1, 3. 3's in both, but that's okay. It just shows up once. 7 is in both sets. It's just going to show up once, though. 8, 9, and 10. Then I take the complement of that. Then I do the complement. And so I take everything that's outside of this A union B setup here, but still in the universal set. And so that's going to be 2, 4, 5, and 6. Next up, same sets here. Now, it doesn't come out and say it, but now you see there's no parentheses here. There's going to be an order of operations, though. The order of operations is going to say to take any complements and do those first. Complements happen first. So it's like parentheses, exponents, multiplication, division, then addition, subtraction. Well, actually now it's going to be parentheses first, anything in parentheses. Then any complements, any complementing is going to happen next. And then finally, you're going to do unions and intersections. You're going to do them from left to right in the order you see them. So when we have A complement intersect with B complement, we're actually going to find the complements first. So if A is the set 1, 3, 7, 9, the complement is everything outside A, but still in the union. So 2, 4, 5, 6, skip over 7, 8, skip over 9, 10, which is that one. Then B complement, take everything outside of B, but still in the universal set. So 1, 2, 4, 5, 6, 9, and that's it. So it's B complement. Then finally, we're going to do the intersection last, and I'm going to figure out everything that this A complement set I just found has in common with this B complement set, which it appears to be the numbers 2, 4, 5, and 6, and never more. And we end up with the set 2, 4, 5, 6. Hey, that's actually kind of interesting. We got 2, 4, 5, 6 here. We got 2, 4, 5, 6 in the previous example. That's actually going to be true in general, and that's something called a De Morgan's law. But we don't necessarily have to go into detail about that. De Morgan's law. Sounds like a really corny TV show. Like a really corny one. Something that I would think of. Okay, so let's compute some of these sets here, and we're going to need a lot of space. Let's see, what's the best way to do this one? I have some ideas. Those shall return soon enough. We will do some of these different ones here. A union B, so using this set here, using this Venn diagram, this is going to be a set bracket. Okay, the elements in A, now we're going to ignore the Roman numerals here. Those aren't actually in the sets or anything. Those are not actually there. Those are just to tell me what the distinct sets are. Why in the world would they use 666? Like what? Like even if you don't think anything about that, like why even do it? It's corny. It's dumb. But anyways, A union B is going to be the set of all elements that are found in A or B or both of them. So again, we're ignoring the Roman numerals. So let's see. Pi makes it in because pi is in the set A. It's not in the set B, but that's okay. Basically, A union B is going to be any element that's in these three pieces right here. It's going to be in there. So pi e, which is actually the constant e, root 2, square root of -1, which we're going to later learn is called I. This thing, e to the pi I, 10 to the 100th power, which is a really large number. And then 2 to the NO power. That's kind of something we glossed over, but just think of it as an object for now. That is going to be my set A union B, just from the Venn diagram. Okay. Let's see what kind of math magic Josh has up his sleeve. Always he has math magic. Next up, we're going to do A union B, but then complement. So we can actually just look at the Venn diagram here. A union B complement, well, wait a minute. This was A union B, the set with pi, e, root 2, root -1, e to the pi I, 10 to the 100th, 2 to the NO, whatever the heck that is. That was A union B. But now we want to take the complement of that. We want to go outside of that. So basically, we want everything outside of A union B. The only thing that's going to be outside of A union B is the number 666. Which again, I don't know why they used that. That seems like almost like you're being sarcastic or like a little teenage punk, you know. It's 666. But okay, that would be the only thing in A union B, complement. All right, what else does teacher have up his sleeve? I shall use my math magic. And we'll do part C. Part C Weber, if you're a big Happy Days fan. A intersect B. All right there, Pilgrim. Now, A intersect B is just going to be the set of all things that A and B have in common, which is basically the things that are inside here, inside this middle piece here. So it's going to be root 2 and root -1. Pretty good, pretty good. All right, let's see what other sorcery I have in my bag. Next up, we're going to do A intersect B complement. First, we need to look at A intersect B, which is this middle slice here. Then we want everything outside of that middle slice. We want to basically take all the elements and ignore the middle slice. So this is going to be pi makes it in, e makes it in. We ignore root 2, we ignore root -1. We're going to do e to the pi I. We're going to do 10 to the 100th power. We're going to do that weird 2 to the NO power. I don't know what that is. And then the 666 also makes it in there. I guess maybe that's appropriate for Halloween. It just seems so weird, doesn't it? It's like, what are you doing? You trying to make some kind of weird statement or something? Don't be weird. So this would be A intersect B complement. We take everything outside of A intersect B, and that includes this business down here. And so we can actually see if we zoom in on this thing, zoomify. Maybe perhaps we could zoomify one more time. A union B is the set of elements in A or B or both. So that's going to be the regions of 1, 2, and 3, this whole area. A union B complement is going to be the set of elements that are not in A union B, which is only this region 4 here, the number 666 by itself. And we can go down this list here, and we can see all of that. It's all nice and pretty. A complement intersect B, that's the set of elements that are not in A and are in B. So that would be just these 3 here. E to the pi I, 10 to the 100th, 2 to the NO. NO way, Jose, as they say. And then A union B complement, the set of elements that are in A or not in B or both. That's just a lot of, that's just a lot of hoo-ha. I don't understand that. No, that's not true. You can kind of figure out what's in A, figure out what's in outside of B, and then union those sets, those elements together. Okay, now this next part here, this is very true. And we've kind of talked about it already, organizing the set theory with actual English words, what they apply to. The word or in English refers to the union of sets. And remember, it's actually and/or. So this thing is almost right. I just write it directly onto the PowerPoint. It's actually and/or, but you can just say the word or to be concise. So that's the union of sets. So or is with union. And is the intersection. When you say this thing and this thing, you might think you're actually talking about a larger set, but you're not. Because now only certain elements can fit both bills. Only certain elements make sense or can fit both criteria. So and is actually more exclusive. It's harder to be that. And then finally, we can look at a quick example. Let's just copy it. Let's do it on a whiteboard. Together. Some of the results of the campus blood drive survey indicated that 490 students were willing to donate blood. 340 students were willing to help serve a free breakfast to blood donors, and 120 students were willing to do both. Good job, 120 students. How many students were willing to donate blood or serve breakfast? Let me type that down under here. And notice that word or, which is secretly and or. So let's work this one together on the whiteboard. Now you have to be really careful with the wording because it says 490 students were willing to donate blood, right? Now I'm not one of them. I have a severe fear of needles. Yeah, get those needles away from me. Get those, I'm getting the creeps just talking about it. It's okay. I have my NOS energy drink to totally comfort me during this difficult time. NOS energy drink is just delicious. Yes, I'm paid to advertise for NOS, and I'm not going to hide it. I'm not going to hide who I am anymore. Anyways, so of those 490 students who are willing to donate blood, brave souls they are, there's going to be some who are also going to be willing to serve a free breakfast to the other donors. There's going to be some who are willing to do both in there. So the 490 is not just a single slice, it's actually going to be two slices together. Let me show you what I mean. Let's draw the Venn diagram. Now the universal set, where they probably filmed, Frankenstein and Dracula, the universal set is going to be the set basically of all the students in the campus that are involved, whether they're serving breakfast, giving blood, or neither of those things. We don't exactly have a number for that, so it's not the end of the world that we don't know. But let's make a quick Venn diagram. There's going to be A. That's going to be B. That is not a bad Venn diagram for me. And let's inject some color into it. Let's say A is the set of students willing to donate blood. And the fact that it's red is just pure coincidence. I did not intend for that, but it's kind of cool now in retrospect. And then, I can't do that. We'll let the set B. What's a good color for breakfast? When I think of breakfast, I think of orange juice. So we use orange. B is going to be the set of students willing to serve breakfast, whether at Tiffany's or otherwise. So I'm going to go write those in here. This is the set A. This is the set B. And now what I'm going to do is in the individual pieces, remember there's four distinct pieces. There's this region here that's just A, does not include the middle region. Then there's this region, which is the middle region. Then there's this region, which is just the set B without anything involving the set A. Then there's the region that's in the box but outside of the circles altogether. So the 490 students is actually going to be everything that's in the set A, the entire circle, which means the 490 students are in two regions on the Venn diagram. They are found between both parts of A. This region and this region together make up the 490. That's going to make it a little bit more complicated. So I can't fully kind of figure all of this out without knowing what that middle region is. So I'm going to put the numbers in there. I'm going to put the numbers. In the middle region is 120 because it straight up tells us 120 are willing to do both. That's going to be the number of people in the middle. Now, knowing that the region A is split into two different pieces, and this piece combined with this piece together have to add up to 490. Then I'm going to say, all right, this section alone has to be 490 minus 120, which would be 370. And so now if I did the 370, this piece alone plus this piece of 120, that would add up to the 490 necessary to fully encompass all of A. Next up, we know that 340 students are willing to serve a free breakfast. So that would be the entire circle B here. So I don't just write, I don't just write 340 here. I need to do 340 minus 120 again, which will come out to 340 minus 120, a little quick mental math, 220. So we now have the pieces we need. Now, if I were to write a number out here outside the circles, but still in the box, well, what would that number represent? That number would be the number of students who are pretty much staying as far away from the blood drive as possible. They're neither going to give blood, they're not going to help serve breakfast, none of that. They're staying away, which I probably would at least, help serve breakfast, especially if he gets you out of class, right? Oh, I gotta go give cookies to people. Yeah, go pretend to serve breakfast or something like that. Get yourself out of class. Not that getting out. I keep forgetting I'm an educator. I'm not supposed to advocate for that. But no, when you're in high school, yeah, come on. Any chance to get out of class, and we'll jump on it. So we don't need to really know what the number is outside here, because the question: how many students were willing to donate blood or serve breakfast? That is going to be all three of these regions. That's going to be this region, this middle region, and this last region here. It's going to be all of them. It's going to exclude everything outside the circles. So I just have to add up. The answer is 370 plus the 120 in the middle with Malcolm plus 220. And okay, I put on my mental math hat. 370 plus 120 is, yeah, it's 490. 490 plus 220 is 690 plus 20, 710. So there's 710 total people that are going to be involved with this blood drive in some way. Serving breakfast, serving blood. It's kind of a gross way to say it. And also just doing both. We're going to have some people who do that. So there you go. So it's kind of cool. We have a little blood drive example, and we're coming up close on Halloween, which, gosh, I just love Halloween. I've told you guys this, right, many times already today. But that would be 710. If we did not think to compensate and subtract off the 120 here and 120 here like we did, we'd be counting too many people. We'd be counting too many people. Okay, so that's going to be it for chapter 2. But we're not done for the day. We're going to go ahead and start chapter 3 today, just for a little bit. And chapter 3 is going to be a lot of fun. Now, I know you guys get spoiled with me as your professor, because I make math just so much fun, don't I? Well, not really. I don't make the math itself fun, because you can't make the math itself really all that fun. Not really. Not exactly. But I can make jokes that are unrelated to the math, and hopefully you guys like that. So one of the things we can talk about now in chapter 3, the things we are going to talk about, logic. Logic. That is the entire purpose of chapter 3. And logic is really cool. Logic, how do I define logic? Well, you've probably heard of the 3 forms of argument: logos, pathos, and ethos. Ethos, when you're talking about arguments, ethos refers specifically to the credibility of the speaker. For instance, you don't want someone giving you medical advice and they are not a doctor. They have no medical training whatsoever, and they just read stuff on the internet. So ethos is important when it comes to making an argument. Pathos involves making an emotional argument. It's bringing emotion into the mix. And emotion, it can be good or bad. You know, it's like basically when you're a kid and you just cry, you can usually get what you want, unless I'm your parent, in which case crying isn't going to work on me. It's not going to get you out of your chores. That's just life. And then finally, the third argument form is called logos, or logic. And in that argument form, you attempt to make just a good argument that kind of ignores emotion, though that's not the only element of logic. And it also kind of doesn't matter who is making the argument. If I was the biggest, idiot you knew, the biggest dum-dum on the planet, especially, just someone who is really bad at math. Let's say you knew someone and you just, man, you're really bad at math. I thought I was bad at math. You're terrible. If you know someone like that and they come up to you and they say 2 + 2 = 4, are they wrong just because they are traditionally bad at math? No. Is 2 + 2 4? It is. Logic attempts to determine the objective truth of something, regardless of who's speaking and regardless of emotion. If I come up to you and I'm bawling my eyes out and I've had a terrible day and I'm bawling my eyes out and I say, please, 2 + 2 is 5. Please believe me. Are you going to believe me? Does it matter that I'm bawling my eyes out? No, emotion does not count in that sense. Logic attempts to deduce, not always deduce, but it attempts to find objective truth that is true no matter what. That's kind of what we're going to learn here. Also keep in mind, those are just argument forms. Just because you make a persuasive argument does not mean you make a correct argument. You can lie out of your face and say everything that's totally wrong, but if you're crying or you seem like this person who's really smart, people might still believe you. But just because they believe you doesn't mean you're right. So logic would actually give you the tools to determine if something is truth, regardless of the speaker and regardless of other issues, regardless of subjective matters. So with that kind of cool introduction, you're like, yeah, we're going to learn about logic. We got to start small. We got to start by defining something that can be called a statement. Now, you might think you know what a statement is, and it is going to pretty much conform to what you think. But a statement is not just any sentence at all. It's not just any sentence at all. For instance, a statement is a sentence that has to be true or false. It can't be both true and false. No postmodern crap here. It cannot be neither true nor false. You can't have that. It's something that is either true or false. I have $5 in my bank account right now, and I've been there. It's not fun. But that's a statement that's either true or false. Either I have exactly $5 in my bank account or I don't. I have $7 or 32 cents. So a statement is, it's got to be something that you could say that's true or false. Even if you don't know if it's true or false, it's something that you could in theory say is true or false. You just may not have the answer at the moment. And so a couple examples. London is the capital of England, and that happens to be a true statement. William Shakespeare wrote the television series Modern Family. No, he didn't, but it's still a statement. Just because it's false, it's still a statement. Some non-statements, things that aren't statements. Titanic is the greatest movie of all time. That one, you can't come out and say that's true or false because it's just an opinion. And also, it's nowhere near the greatest movie of all time. Also, it's one of the biggest pieces of trash I've ever seen in my entire life, and it won Best Picture at the Oscars in the 90s. Some of you may not even know what Titanic is, and that's okay. Let's update that. I like movies. Let's update that with Star Wars, The Force Awakens. Or you could say Star Wars, The Last Jedi. Or you can say Star Wars, what was it, Rise of Skywalker was the most recent one. Any of those movies you put in there, those are all opinion. Now, as a little joke real quick, as a side joke, yes, that's opinion. You can't say it's true or false definitively, objectively, right? But in fact, none of those movies are anywhere near the top movies of all time. Star Wars, The Rise of Skywalker is an abomination. Star Wars, The Last Jedi is a slap in the face to people who like Star Wars. Star Wars, The Last Jedi is literally the creators of the movies, the new movies coming out saying, if you like Star Wars, you can go to HE double hockey sticks. And you know what a hockey stick is? It's the letter C. You can go to heck. No, Star Wars, the most recent Star Wars trilogy is the biggest piece of trash on the planet. And you know what? I'm going to keep talking about it. Star Wars: The Force Awakens, I went into that movie. They did a 6-movie marathon featuring Star Wars, the prequel trilogy, episodes 1 through 3, which I love those movies. They're not great, but I love them. Then they did the original trilogy, you know, The New Hope, Empire Strikes Back, Return of the Jedi. So I'm hyped up on Mountain Dew. It starts at 3 in the morning, and then they did the 6 movies, and then the new movie, Star Wars: The Force Awakens, which I hadn't seen a Star Wars movie, a new one, in over 20 years. That thing comes, or not 20 years, what was it, like 15 or something like that. Anyways, that thing comes onto the screen. I'm about as excited as I've ever been in my entire life. It's been like 16 hours I've been sitting in this movie theater watching movies. And Star Wars: The Force Awakens comes on. And spoiler alert, they kill off Han Solo, and Han Solo is like my childhood. It's Harrison Ford is the greatest actor of all time, and they kill him off for some stupid twist. That movie can go to HE double hockey sticks. I'm very passionate about Star Wars, in case you don't know that. I read a lot of the books. Have I been reading some of the Star Wars comic books recently? I don't want to admit that in public, but yes, I have. Yes, I have. Anyways, so these are all opinions because they're just statements. Sorry about that. You can see the passion flowing through me. So it's just an opinion, it's not a statement. Read pages 23 through 57. That's just someone telling you to do something. You can't say that's true or false. Read pages 23 through 57. False. No, that's not what you'd say. You'd say, I won't do it, but you can't exactly say that's false. And then certainly a question is not a statement. Certainly a question, not even the Charleston Comics character who would later become Rorschach in The Watchmen. That's not a statement. So we use a statement. A statement is going to form a basic building block of some of the logic that we're about to do here. It's really convenient. We're going to have to evaluate the truth of certain statements. London is the capital of England. Well, evaluating that thing's truth, it's hard to say how you do that exactly. You'd go look it up maybe. William Shakespeare wrote the television series Modern Family. I'd have to go look up every writer of Modern Family, or I'd have to realize Shakespeare died in the 1600s, well before this show came out. So what we do is whenever we're trying to assess the truth of these, it can be a pain in the butt to have to say the entire statement every time. So instead, we're just going to use simple symbols. P, Q, sometimes R, sometimes S. And those just represent statements. Just like X and Y can represent variables in math that are secretly numbers, P and Q, we're going to use that. So instead of saying something complicated like London is not the capital of England and William Shakespeare wrote the television series Modern Family, I can just say not P and Q. We're going to have all those symbols here by the end of chapter 3 that we're going to use. So we're just going to symbolize P, Q, boom. That's what I like about Texas. Yeah, exactly. Yeah, it's just arbitrary. It's for this particular example, P and Q are the statements, London is the capital of England, P, William Shakespeare wrote Modern Family, Q. But in another example, we might have 3 different statements. And yeah, it's just to differentiate them. It doesn't even matter that one's first, second, or third. It's just kind of consequential. Exactly, just like variables. That's pretty much really all it is. You'll also notice that between what we just did in chapter 2 and what we're doing here in chapter 3, there's almost very little numerical math involved. Remember, we talked about math is not just numbers. We assume it's just numbers, but that's just not the truth. Math is actually logic. This is actually closer to more abstract and true blue mathematics than you believe. All the numbers and stuff is almost just stuff that came about because of all this logic here. So that's kind of an interesting little point here. And again, I'm real passionate about this stuff. I love this kind of stuff. And then when we get into chapter 8 and we're talking about money and we're talking about calculating the payment on a mortgage, how to grow your bank accounts, how to prepare your taxes, ooh, I'm in heaven. I love that. I love it so much. I love talking about money. Why do I love talking about money? Because I truly believe with all my heart that money is the most wonderful thing in the entire world. It's better than love. It's better than any of the more recent Star Wars movies, but that's not very difficult exactly. No, I'm just kidding. Money's not the most important thing in the entire world, but it is important to manage your money. So when we get to chapter 8, which is actually going to be the next chapter we skip over some in that book. We're going to get right back into this looking like a math class. But for now, this kind of doesn't look like a math class, but secretly it is. It's just you have to expand your idea and your definition of what math is. So we're going to learn some of the operations you can do with logical symbols. And it's actually a perfect analogy to what we just did in chapter 2, set theory. The first operation you can do with symbols is you can negate them. You can negate them, which is exactly what it sounds like. The negation of a true statement is basically the opposite statement and it's false. The negation of a false statement is its own opposite, it's true. So the negation of London is the capital of England the negation would be London is not the capital of England. It's just to take the exact opposite stance that the original statement took. And I mean exactly the opposite, nothing left on the table. If Q is the statement, William Shakespeare wrote the television series Modern Family, which is false, then not Q, the negation of Q would be William Shakespeare did not write the television series Modern Family. You just got to change the verbiage a little bit in the conjugation of your verbs. And so suddenly that becomes a true statement because it started off false. So a negation is nothing more. Negation is just taking the opposite stance of the original statement. That's all it is. So we kind of already went through this. Shakespeare did not write this TV show Modern Family. And suddenly that becomes a true statement. It was false to start with. No, he didn't write Modern Family. He didn't write anything of particular notice, except for Hamlet, Macbeth, Richard III, some of the finest poetry you'll ever read, only some of the best stuff ever put to paper in the English language. But other than that, Shakespeare was a hack. None of his writings are any good, except for, some of the greatest classics of all time. But anyways, he didn't write Modern Family. So what we can do is we can take some of these statements here. I'll give myself a little extra space. Speaking of space, there's a Space Jam 2 coming out with LeBron James instead of Michael Jordan. I'm kind of excited about that. Random thought for the day. Today is not Monday. So if you're taking the stance, today is not Monday, its negation is very simple. I'll use it in red. It's just take the opposite stance. Well, today is Monday. It doesn't matter if it's a true statement or not that you're crafting. We're just taking the negation of it. Very simple. Now the next one, it's not always just put the word not in there and suddenly it's a negation, or take away the word not. You have to really be sensitive to what you're reading. You have to really be careful and hone in on what you're reading and just take the opposite stance. Even if you use a slightly different wording, that's okay. As long as the sentiment is there, it's logically the same. So here's a doozy. It is not true that today is not Monday. But it is not true. So it is not true that today is not Monday. Correct. So the sentiment of that statement is that today is Monday. And if you think of things like the double negative, you use not here and you use not again. So the nots kind of cancel each other out, kind of. And so the real thing is that it is Monday. So this thing here is just saying it is Monday. So the negation of that statement, you can take away all their wordiness and just make it today is not Monday. I guess I should capitalize Monday. The M in Monday. And then the last one is pretty darn simple. Today is Monday. The negation of that is, again, today is not Monday. I don't know why that's even on there. What that means is that this statement, today is Monday, is logically equivalent. It's the same thing as saying, it is not true that today is not Monday. It's a very wordy way of saying the same thing. And we can take their negations. So again, negation is a simple concept. How many of you want me to open up your minds a little bit? How many of you want to hear a cool little fact? You ready for it? You guys ready for a cool little fact? I hope you are. What we're going to learn is that everything we just learned in chapter 2, set theory, has an almost exact analog, I should say, in chapter 3, logic. The negation in logic is the exact same thing as the complement in set theory. I'll even write that because that's really slick. The negation in logic is fundamentally, meaning it may not look like it, but it's secretly, truthfully the same thing as the complement in set theory. In fact, what we're going to learn is that logic and set theory are secretly the same thing. They're just different expressions of the same idea. Just like 1/2 is the exact same as the fraction 3/6. Do you have a question? Oh, it looked like you're about to. No, you're good. You're good. I was just making sure. So the negation is the same as the complement. They form the same idea. Moving right along. Whenever we want to take the negation of a statement and we want to express it concisely, we just use a tilde in front of the letter itself, a tilde. So a tilde, you hit shift and then you hit the button that's like above the tab on the very far left of the numbers. That's where it is, at least on mine. And you can do that R. If your statement was R, then putting a tilde in front of it means not R. So if the statement P is Shakespeare wrote Modern Family, then the statement Shakespeare did not write Modern Family would be symbolized not P. You'd put a tilde in front of a P, and you literally read that. This is read not P. If your original statement Q is that today is not Monday, just because it has a not in it doesn't mean you're going to put the tilde in front of it. The original statement is that today's not Monday. So then the statement today is Monday is the opposite stance. So this one is not Q. It's the negation of statement Q.